Troy Thornberry is our speaker today. Troy has degrees from across the Midwest, from a BA from Lawrence University in Appleton, Wisconsin, a master's from Iowa State. University of Iowa, yeah. And a PhD from University of Michigan, where he received an outstanding grad student award. And then, what's that?
Back in the dark ages.
And then, well, he's received many awards since then, but he did a postdoc at University of Toronto, and then came to Boulder in 2003, and has been working at NOAA on field campaigns, on the PALMS instrument, on ATREX and Global Hawk and Poseidon missions, and the upcoming Night Fox mission.
Changing scales.
And he's here to tell us about what he's found.
All right. Well, I'd like to thank everybody can hear me? I'd like to thank the organizers for inviting me to give this talk. I'd like to talk to you a little bit about a number of the field campaigns I've been involved in recently, mostly under the tutelage of Eric Jensen, who's in the audience. Yeah, I came here working on tropospheric aerosols and have sort of wended my way up in the atmosphere, and am now looking at more physical processes in the tropical tropopause layer, lower stratosphere type of thing, just trying to move up in the world. What I'd like to talk about are some perspectives that we've derived from in situ measurements in the tropical tropopause layer, dehydration processes in cirrus clouds, and how it affects stratospheric water. I think that a number of people in the audience and here know a lot about. So, quick outline. I'll start with some motivation for those that aren't really vested. Sort of atmospheric water vapor, why do we care in the climate system? Particularly, why do we care about it in the TTL in the lower stratosphere? Why there's any lack of understanding in what's going on there. And then results from the ATREX mission that Mike mentioned on the Global Hawk, particularly in 2014 in the Western Pacific, and then the Poseidon mission in 2016 on the WB-57, and then just a quick summary. So water vapor in the atmosphere. Water vapor is the dominant greenhouse gas in the atmosphere. It's just not one you necessarily think about in terms of when people are talking about global warming, because we don't control it other than indirectly. It's responsible for approximately half of the climate sensitivity in the climate system. So we double CO2, we'd get some warming. Water multiplies that by a factor of 2. In the troposphere, where most of this is occurring, basically the relative humidity as the climate warms is expected to remain constant. So we'll increase the absolute humidity, which increases the global warming from the water vapor. It's generally agreed in theory and in models, so all that's good. Much smaller amounts of water are in the upper troposphere, lower stratosphere, the TTL, but they're still important for climate systems. So some recent modeling indicates that water vapor itself in the TTL, in the lower stratosphere, about 3 watts per meter squared per Kelvin feedback. And then it also has an indirect effect through cirrus cloud formation that contributes as well. And cirrus clouds, the thin cirrus clouds in the TTL are unlike the sort of the blanket of clouds. Instead of cooling, they're actually a warming cloud. Water vapor in the atmosphere. So here's on the left is a balloon sonde from Guam in 2016. Temperature decreases up to the tropopause, somewhere around here in the tropics, and then increases above that. Water vapor responds. It's physically controlled, unlike a lot of the trace gases we measure. It's physically controlled through condensation processes. So basically, it decreases following temperature, following the saturation. Its saturation as a function of temperature to the sort of cold point, and then pretty much straight above that, or increasing eventually through chemical production. So this black line shows the integrated column water, and it starts at 0.9. And so basically, by the time we're in the free troposphere, all the water in the atmosphere is already there. Why would this matter all that much? If you look at it from an outgoing long wave radiation perspective, so staring down at the Earth and looking at the sort of long of 6 micron terrestrial long wave radiation, what's cooling the planet, you can see the effect where methane and water here, significantly, you know, if you were looking at those wavelengths, you would not even see to the ground because you're just going to get saturated in the water. So even small amounts high in the atmosphere have a significant effect. So water getting to the stratosphere, that process usually is occurring through vertical transport in the tropics, and then it spreads out through the stratosphere. So tropical processes are really what we need to study in order to understand that. Some of the significant work, Holton and Gettleman, basically as the air goes up, once it's above the level of deep convection, it starts to rise more slowly. It has the opportunity to go around the planet, find the cold spot, dehydrate to those temperatures. Plot here, Eric and Bill in a paper basically showing that if we look at the tropical tropopause temperature, especially if we look at those sort of these colder regions, we can understand a lot of the variability, both on a seasonal basis and on an interannual variability, interannual basis. And Andy Dessler has done some sort of parameterization, looking at a couple of things that should tie into that, and can do a reasonably good job of reproducing the variability of water vapor in the lower stratosphere. But one of the things to focus on is that, so these are done in anomaly space, and generally the agreement of getting the absolute value of water in the lower stratosphere has been something more of a problem than getting the variations. So we know what's controlling it. It's these tropical tropopause temperatures that are controlling the water vapor, but exactly the relationship between those two, that's where this dehydration process sets in. So just another slide on sort of the radiative impact. So balloons from Boulder, looking at water vapor over a long time series, and the frost point sondes here, you see some fairly significant changes. Those were modeled by Susan Solomon's group, and basically showed that even though we're talking about just a few parts per million relative to the 20 or 30,000 parts per million that are at the surface in the tropics, it can have a fairly significant impact on the radiative balance and the climate system. So dry air conditions, we're talking about a few parts per million, a factor of 10 to the 4, well, a factor, 10 to the 4 lower than what we're seeing down here at the surface. But still, it's parts per million. We make measurements regularly of trace gases that are in the part per trillion to part per billion range, not a problem. Why would it be any issue to measure the water vapor here? And one of those issues is that there is so much down here, and it turns out that water is a fairly sticky molecule. Over the past several decades, we've put research-grade instruments on planes, and we've flown them up there, and we've made measurements. You have two instruments that say, well, I'm making a measurement that's good to 10%, and they disagree by 50 or even 100% in some cases. So here you can see there's a campaign in Costa Rica and another one in 2 different seasons, and significant disagreements on the order of 50 or 100% between these instruments. And that has an effect. So looking at a snapshot of one of those in a paper that Eric wrote, we have the water here plotted as relative humidity, and these are the saturation lines. So basically, this is where theory tells us we should have nucleation, clouds should form, the water really shouldn't go that much higher. And we're looking at relative humidities that are over 200%. And that caused a lot of sort of head scratching and people to think, and a paper that came out when dry air is too humid, trying to understand what would be interfering with this cirrus cloud nucleation process that would keep the water from really ever getting this high. So the way we got into this game is that as the community was trying to figure out why these measurements weren't working and why there were these disagreements, we were motivated to try our hand with the hubris of the aeronomy lab at the time that we could make the better measurement. So ultimately we developed this instrument. It's a tunable diode laser instrument. We added a second channel so we could measure condensed phase water as well as water vapor. But we came at this from real trace gas measurement perspective. In other words, we're used to building things to measure part per trillion, part per billion type of things. For the constraints of the Global Hawk, we had to build a small instrument. We built it very compact, put a lot of things in there. One of the things that we did is we included an onboard calibration system. So none of the water vapor instruments that were out there flew an onboard calibration system. So they measure on the ground, they're like, okay, here's our calibration. They go and they fly in the atmosphere. They're like, okay, here's the answer. And they come back, look, we have the same calibration. But not knowing exactly what is happening in between those 2 points seemed to be a significant issue. So we put together an onboard calibration system using the reformation of the oxidation of hydrogen in air on a platinum catalyst to produce water on demand that we could deliver to the instrument. We ended up with sort of overall uncertainties that are on the same ballpark as these other instruments, but we have something that we can really tie it to. We operate the instrument in a sort of constant pressure, constant temperature, constant flow environment situation, such that it takes off, it doesn't even know where it is. It could be on the ground, it could be at 80 hectopascals in the atmosphere, and it shouldn't know the difference. And then we can verify that operation with this calibration. So the first thing we did was we put that on the Global Hawk. We flew it in the Eastern Pacific over here in 2013, and it worked well. 2014, we put back on the Global Hawk, flew it to Guam, and sampled this region in the Western Pacific that is sort of the key to understanding where the final dehydration of water that's headed for the stratosphere occurs. We covered, the Global Hawk has the advantage that it's a really long endurance aircraft, so we were doing 16 to 24 plus hour flights. We could get a lot of sampling in. This is a shot of the Global Hawk for the first time landing outside the continental US, landing at Guam. This was one of the only times we actually saw it in the air in the day due to some communications difficulties. We were typically trying to take off at 2 or 3 in the morning, and so this is what the plane usually looked like at that point. So in terms of water, we had 2 instruments. We had our instrument, and then there was the NASA Langley DLH instrument, which is an open path TDL. They shoot it out. They've got an 8-meter path length, reflected path length. Shouldn't have any issues. So now we're flying 2 instruments, in spite of the fact that, in the past it's always been an issue. So when we look at how well we agreed over the range of water vapor that we saw in the tropical tropopause layer, basically we had exceedingly good agreement. This is a frequency distribution within each sort of ppm of water. It's on a log scale. So really we're concentrated right around here at a ratio of 1 between the two. Here's the median absolute difference between the two in percent. So even down here, when we're measuring 1 to 2 parts per million, on average, we're within 10% of each other. So this is just much better than was ever accomplished in the past, and gives us a lot more confidence in that the measurement that we're making, which we thought was good, and agrees with theirs. In terms of sampling, basically we're talking about altitude range between 14 and 19 kilometers. So the aircraft operates from down here at 45,000 feet and then climbs up to a maximum altitude around 19 kilometers. Spend a little bit of extra time down here after we descend, and then level flight, and then climb back up. So we spend a lot of time just doing vertical profiles through this range. In the Western Pacific, this area is dominated by persistent cirrus clouds, so we're flying in a lot of clouds. And it's just what the distribution looks like in terms of potential temperature space. So the one thing that we were really hoping to target were these coldest temperatures down here in the neighborhood of 185 Kelvin. And due to operational constraints, we didn't get as much sampling down there as we really would have liked. But we got a lot of sampling in the sort of cold TTL region below 195. In terms of the cloud sampling, as I said, we were in cloud a lot of the time. Very ubiquitous cirrus cloud in this region. So more than up to as high as 30% of the time we're in cloud. Across these altitudes, and this sort of in terms of one of the issues with an aircraft campaign is when you're chasing features or things like that, how representative is your data really? But the sampling that we had here is actually fairly consistent with what Calliope would indicate as a typical frequency of occurrence of cirrus clouds in these altitudes. So the red box here shows the altitude and latitude range in which we were operating. And the peaks here kind of match the peaks in our sampling. One of the things to note is that down here at the coldest temperatures, we saw a lot of clouds. And that's really kind of what you'd expect. When you're at the coldest temperatures, that's where you're getting that final dehydration, and that's where that water is finally being pulled out. So more frequent clouds down there. But again, not as many samples down at those temperatures that we really like. This is a plot of the sort of distribution of relative humidity as a function of temperature. This is the way that these things have been looked at in a number of cases in the past. And one of the things to note is that here in clear sky, so outside of cloud, looking at the relative humidity distribution, we really didn't see any measurements that were significantly above that homogeneous freezing threshold. So the measurements that we made in agreeing with DLH, basically we're saying that it looks like physics is more or less as we expect it to occur, and that there isn't anything that's really strange going on, at least in the regions that we sampled. Here you see the sort of elevated relative humidity at these warmer temperatures. This is the dominant convective outflow region. So this is where the convection is tending to dump out a lot of water, significant hydration. This is near the bottom of our profiles. And then we'd go from here and we'd climb up and we'd get dry, and then the relative humidity would increase as the temperature decreased. Looking in cloud, so one of the other things is that, looking inside a cloud, you would expect the water to be something closer to relative humidity with respect to ice of 1, or in this case 100%. And that's largely what we saw, although we were sampling clouds that were clearly growing, clouds that were sublimating. And we did see a few sort of questions as to how much of it falls within instrument precision, really high values, which are possible, perhaps even cloud, even though you'd expect the homogeneous nucleation to really kick in there, as it was observed to on some occasions. Focusing on the cloud particles, we had the SPEC cloud probe suite making measurements in 2014. And generally what we see is, compared to the mid-latitudes, we're looking at smaller cloud particles. These are low water vapor, cold temperatures. So at the coldest temperature, sort of below 190 Kelvin, we're looking at particles that are, the largest particles we were seeing were a couple hundred microns, but there were very, very few of those. It was dominated by particles that were less than 15 microns, so small cloud particles, and even the mass was dominated by sub 25, sub 30 micron particles, which has implications for dehydration. In terms of cloud number, the clouds tended to be quite sparse. The blue is a distribution from one of the cloud probe instruments, and the red is sort of the cumulative frequency distribution that we observed, and 90% of the clouds that we saw had fewer than 100 cloud particles per liter, and a very, very, very small fraction, which likely corresponded to fresh nucleation, homogeneous nucleation, nucleating event clouds had more than 1,000. So the implications of both the small cloud particle size and the sparse clouds has to do with how long it takes to draw down the supersaturation. So the temperature drops, you have either ascent through generation of cold air or wave-driven cooling. You have cold temperatures, you drive supersaturation, you start to form a cloud. How long is it going to take that cloud to actually pull the excess water out of the air and into condensed phase, which could then be removed? So that's basically a function of the sum of the number and the particle radius. And if we plot that for all of the clouds that we observed, we see that at the sort of the lowest altitudes, the relaxation time that it would take to draw the water down to saturation is on the order of tens of minutes. But then as you get colder and colder, as we go up in altitude, we start looking at this process taking hours, multiple hours to occur, so that if you have something, a temperature perturbation that is sort of on that time frame, you could actually form the cloud, it starts drawing down the relative humidity, but then the temperature could turn around and start warming up before you actually get all of that water out, and you wouldn't completely remove all the water that you would have thought based on the temperature that you reached. So looking at those different processes together, we had the relatively frequent supersaturations in clear air, where the temperature got cold enough that we had supersaturation but did not in fact form a cloud, whether that be a heterogeneously nucleated cloud or homogeneously nucleated cloud. So we could clearly see that in this case, you could drive supersaturations and not actually remove the water. Even when we did form a cloud, often the time that it would take to suck all of the water out into the condensed phase was long enough that might not have successfully removed all of the water. And then the fact that we're producing these really small crystals, they will separate from the air that they're formed in, but they're not falling all that fast. And the time that it would take them to move kilometers is long relative to their likely lifetime. And so they're likely to sublimate, and that water will move down somewhat, but not all that far, and then be available for sort of continued uplift processes. So all three of these mechanisms are sort of the process level indications of why dehydration at these temperatures is not a perfectly efficient system. So you can't simply say, okay, what was the lowest temperature that you saw? I can tell you what the water is, because these processes all act against that efficiency, particularly at these low temperatures. So trying to understand exactly how we get down to the couple parts per million, 2 to 4 parts per million that's entering the stratosphere. These are limiting the efficiency of the process. So if we look at those from sort of an individual perspective, we've got this sort of process level understanding that the in situ measurements are really good for. But how do we take that and then expand it to sort of a larger understanding? How do we use that in conjunction with a satellite observation or with a model or something like that? So in this region, this is just a plot showing from a recent paper from Thomas Berner's group when he was at Fort Collins, that error interim in this case is getting the water vapor amounts right, although not the dynamics. So there's a question of, do you really get the dehydration right? Do you get the large scale dynamics right? Global models certainly aren't going to capture the smaller scale dynamics. So how do we take a picture like this and try to figure out, is there any way that we could make some improvements in that or increase the understanding or parameterizations that would lead to a better prediction? Overall, just a comparison of how well the reanalysis can do compared to our fine scale in situ measurements. So in this case, looking at temperature, so this is temperature measured by the MMS meteorological suite on the aircraft, and then compared with a 4D interpolation from era interim and say, okay, fine, how close are they really? And the agreement is really quite good through most of the troposphere, starts to break down around the tropopause with some variation. And then in 2014, but not in 2013, we saw this sort of move away from agreement at the highest altitudes. Looking at that in terms of as a function of temperature, so if you look at this in color, warm down here, cold up here, you notice that the coldest temperatures are all clustered over here, where the aircraft measurement was lower than the reanalysis, as you'd expect. So you can see that here as a function of temperature. At the coldest temperatures, you start to see a positive bias. But that's just a scale question. I mean, we're making these fine scale measurements on processes that are smaller than the model is really capturing. So the question is, can we use our in situ data, can we use the reanalysis and try to sort of get a more global picture of what the dehydration effect is? So in order to do that, what I did was looked at a series of back trajectories. So from points all along our flight track, run a cluster of back trajectories to try to capture some of the dispersion because back trajectories are a far from perfect thing, and determine what, based on that, we would expect the water, how we would expect that the water to have been removed. So in this case, for each point along the flight track in an altitude range above the final dehydration, so above the highest clouds that we observed, run a back trajectory until the point where that trajectory looks like it interacted with some convective process, so near the top of a convective cloud, and then say, okay, fine, it could have been influenced by a convection at that point. Then we walk it forward, trace that forward until we find the point at which it reaches the lowest saturation vapor pressure, and say, okay, fine, that would, if this were a perfectly ideal system, that would be the amount of water that would continue on into the stratosphere. Then what we can do is we can compare that value that we determine there with the value that we actually measure and say, okay, how well does that really agree? So in each of these, we did a cluster of 25 back trajectories and took the average of those values and then compared it to the measured value. This is just a map showing the location where those coldest or lowest saturation mixing ratio points were reached and the temperatures at which they occurred. So basically, as expected, they're all clustered here in the Western Pacific, the cold trap. Those dehydration points tend to occur near the climatological cold point tropopause, with some excursions about that. And the temperature was typically on the order of 187 Kelvin. So using those two things together and looking at the minimum saturation mixing ratio, the distribution centers around 2.1 parts per million with a range of about 1.5 to 3. So those would be the range. Those would be the stratospheric entry water vapor that would be predicted by a trajectory running through the reanalysis world. If we compare that to what we actually observed, we see that we're at a value that's more like 2.7 parts per million. With slightly skewed distribution here. One of our flights during Guam, we were sort of in one space, so we sampled that space really, really well, and that leads to a bit of a sampling bias right here. But overall, we're looking at sort of a 2.7 to 2.1 part per million difference. Just taking the ratio of those, it would indicate that the trajectory minimum is only about 80% that of what we actually measure. So in terms of trying to put a ballpark net number on the inefficiency, it's on the order of 20–25% that excess water that makes it past versus what a trajectory model would predict based on the temperature field that it's traveling through. So that's sort of the ballpark number. And then what we'd like to do is figure out if there's some way that we can take this sort of information, particularly maybe looking at this as a function of temperature, any way that we can sort of improve the parameterization within the model to get the model allow the model to do a better job of getting the correct absolute value of water getting into the stratosphere. So one of the things is, this is just walking through the generic, the reanalysis error interim in this case. There are indications that, there are certainly things that are missed, and one of those, June Kim and Joan Alexander have a parameterization that would allow there to actually be colder temperatures due to small scale features that would actually exacerbate the problem. So changing gears, so from 2014 to 2016, we went back. This was in October instead of January. And flying on the WB-57, one of the things that allowed us was we had the opportunity to fly much closer to convection.
Actually, can I ask you a question?
Sure.
Before you move on?
Sure.
So the waves are obviously not resolved. They're
Right. Right.
It would actually make it drier.
Yes.
So the discrepancy would be
It would exacerbate the bias. Yes.
Have you tried to estimate? I mean, we have some idea of the amplitude of the waves.
Yes. So Ray and Lenny ran some trajectories for me, and it's another 5 to 10% dry bias.
Thank you.
Yes. So switching gears, Poseidon. So one of the things about the Global Hawk is that there's no pilot. There's a limited situational awareness, and they really don't like to fly anywhere near bumpy conditions, convective clouds, and things like that. So we tended to stay away. We did do one flight where we sort of skirted around a typhoon, but in general, we were not flying anywhere that there was a chance the plane could encounter convection. With the B-57, you've got a pilot and a backseater. The pilot's there, he can make his own decisions. And sometimes we're like, oh, we don't think you want to go there. He's like, it looks like it'll be fine. We'll just fly right through. So we did a lot more sampling close to convection than we were able to during ATREX, which gives us a somewhat different picture. So we had sort of the broad scale. ATREX, we're looking at time since convection of the air in the order of a day to 5 days. Here we were actually flying sort of in between or directly above collapsing convective systems, getting much closer to the convection. So again, because we hadn't spent enough time in Guam before, we went back to Guam, made a series of flights. This was a dual purpose campaign. We had a new SO2 instrument that some of you may have heard about. Drew Rollins spoke here earlier. So one was to look at sort of the potential sources of sulfur dioxide in the TTL, and the other was to look at cloud processes in a more convective environment than we'd been able to before. Just sampling, again, we like to cause the pilot some grief. We're like, go out there, but you don't get to fly level. You're going to fly up, you're going to fly down, you're going to fly up, you're going to fly down. Only occasionally does a backseater get sick when we make him do this. But they did a great job of sampling a range of latitudes and longitudes, giving us really nice vertical profiles through the TTL, and again, sampling a lot of clouds. So looking at the ice water content, so this is from the other channel on our water instrument, we're able to measure the ice water content expressed here in parts per million. So this line right here is typically sort of as low as we were flying. And you can see that sort of from 13 to 16 kilometers, we see these relatively high ice water contents on occasion. Above that, it's a very compact distribution. Looking at that in terms of a real statistical distribution, you see that the clouds down here had 20 plus parts per million of water, whereas up here we're looking at a few parts per million of water. So we were operating an ozone instrument on this flight as well. So had quality ozone measurements that we were relatively happy with. And looking at the distribution of in clouds, here you can see the gray is all of the ozone that we measured. The colored markers are the ones that were measured inside cloud. So you can see they both sort of follow the same general trend with the highest clouds we were measuring were up to 18 kilometers in altitude. When we look at it in terms of an ozone distribution, looking at in cloud, we saw an interesting thing that basically at altitudes from our lowest sampling around 13 kilometers up to 16 or a little above kilometers, we see this strong mode in the distribution at 20 or 10 to 20 parts per billion of ozone. So this is sort of representative of what you'd expect ozone to be from the tropical tropopause layer, the tropical marine boundary layer. So this is air that's basically being pulled up through deep convection, and then we're measuring the cloud, and we're seeing these really low values of ozone. Above that, we see a shift over to higher values, and then it starts to follow the regular ozone curve you'd expect in the upper troposphere. So here, just saying that this, it's typically below 20 parts per billion, up to about 16 kilometers, and shifts. And so one of the questions is, can we actually use ozone in this case, because it's a tracer that has different properties at low altitude and high altitude, as an indicator of whether we're looking at a convective cloud or a non-convective cloud. Just for comparison, in the clear air ozone profile, you see that values were typically, throughout the depth that we were sampling, more like 40 parts per billion, and then at higher altitudes, they follow the general curve up toward the stratospheric values. Breaking those down into individual sort of kilometer, or in this case, half kilometer bins, and looking at the ozone distributions. So down here at the lowest altitudes, 14.5 to 15, up to 16 kilometers, see the strong mode that's occurring at 20 parts per billion. It's representative of the marine boundary layer that's being pulled up with some higher values. Comparing the in cloud in blue to the clear air in red, you can see that this has significantly lower, or a stronger mode down here at this low value than is typically found in the clear air. Changes as you go up in altitude. So in the sort of 16 to 16.5 kilometers, it's starting to look somewhat bimodal here. The clear air is showing a value shift upward in value, and some of that's being reflected in the in-cloud values, although there's still a strong mode down here, 20 to 30 parts per billion. Above that, and the two distributions start to look considerably more similar, sort of a broad distribution smeared out. The clear air is typically always somewhat higher than the in-cloud, but there's a shift away from this sort of marine boundary layer air toward more represented values of the upper troposphere and lower stratosphere. If we switch and we look at that in terms of temperature, so these are the temperatures measured in cloud or in clear air for these these altitude bins. You see sort of a bimodal distribution down here at the lowest altitudes, but the in-cloud and clear air are pretty much identical. So in this case, the conclusion we would reach is that what's controlling the formation of clouds, or the presence of clouds at these altitudes, is the presence of water and not so much the temperature, because the temperature is really the same in cloud and out of cloud. It's a difference in the amount of water that's driving whether there's a cloud or not. As we go up in altitude, you start to see a change. At above 16.5 kilometers, you start to see a separation where the clouds are really occupying the colder temperature space relative to the clear air. In this case, we conclude that it's really a temperature that's driving that cloud. And so what we may really be looking at is this change from a convective cloud bringing up excess water that's down here to a cloud that's forming due to the temperature being colder than the surrounding environment. So this is a cold spot where that cloud is forming, and it's temperature driven. So looking at the total water, so this is a combination of the water vapor and the ice water content. Down at these lower altitudes, the clouds tend to be somewhat juicy. They tend to have more water than the surrounding air. And as you go up in altitude, those distributions become more compact and similar between the two. And even at the highest altitudes, it looks like you might have lower total water content in the coldest in the clouds at highest altitudes. That sort of representation is the dehydration that's going on. So the conclusion that we're trying to reach is that these clouds down here are convective deposition of water into the TTL, whereas these clouds up here, which are the ones that had the higher values of ozone, no longer those boundary layer levels of ozone, are indicative of in situ formed clouds and representing dehydration of the air on its way to the stratosphere. And in some cases, you look at that and say, okay, if we're looking at trying to sort out whether there are these two processes and whether we can use ozone as a discriminator between them. And one of the things that's confusing is that as we're flying, an individual profile, so this is just a snapshot time series across here looking at these sort of individual measurements of ozone, where the larger circle is in cloud and the thin line is the clear air. You can see that we start at these low values. In this case, there's a gap, and then we hit another cloud up here. But on some of the profiles, we go from high ozone values. So this is nearly stratospheric levels of ozone up here where we're in cloud at high altitude. And we descend, and there's more or less continuous decrease in ozone as we go down, reaching these low 10 to 20 part per billion levels in the lower cloud, but without seeing any strong segregation between the two. So it's not like, okay, here's a convective cloud, then there's some clear air, and then we go into a cirrus cloud, and that's the in situ one. Really looking at those from a larger perspective, if you're looking at it from a satellite or something like that, it's just a continuous cloud. And what we can say, though, is that it has radically different levels of ozone, and those seem to indicate that while this down here is likely a convective cloud that's brought up air and you're dumping water into the TTL, continuously above that you have these cirrus cloud that's actually acting as dehydrating the TTL, dehydrating that air on its way to the stratosphere. So to sum up, looking at these two missions, we've got a lot of sampling time in the Western Pacific, this critical region for understanding water transport to the stratosphere. In ATREX, we did a lot of cloud sampling, but it was largely non-convective. The sampling statistics were not dissimilar from what you get from a satellite observation in the region. We saw a number of things where we can investigate the process level understanding of dehydration and say there are reasons why this dehydration isn't sort of a perfect process. That if you run a model, and so historically a lot of these models go, okay, fine, we hit 100%, we form a cloud, that cloud removes the water, and then that air continues on with the water that has left. But there are a number of reasons why that is not a perfect process. And then we're trying to figure out, is there some way that we can use this sort of increased process understanding to parameterize something that could go into these global models in a sort of computationally efficient way that would allow a better absolute prediction of water reaching the stratosphere. As can be done with other models where you have the time to spend running the back trajectory and running a real cloud microphysics model and things like that, so where you form it and you remove it and you follow that whole process as you go along. Is there some way that we can sort of use an overall picture that we could deduce from this to parameterize it so that it could be used in a large-scale model? And then the other thing that we looked at, we went back in 2016 with the WB-57 flying in this region and with an ozone measurement. We saw this discrepancy or this discontinuity in the ozone distribution between these lower clouds and higher clouds that looks like we could use that as a discriminator between convective clouds that are adding water to the TTL and in situ formed cirrus clouds that are removing it and performing the dehydration of that air as it's reaching the stratosphere. So outstanding questions there. Are we really thinking about convection the right way? Is there some process where this is actually still a convective cloud that's still pushing up water, but we're seeing this increase in ozone due to further entrainment at higher altitudes? And we need to sort that out as to whether or not we can really use this as a good discriminator or not. So combining the analysis using the ozone, and start looking at some of the other data, looking at the cloud particle number and size distributions to see whether or not we can see additional differences between those clouds that would give us more evidence that we're really looking at two formation processes of those clouds. And then also possibly some other short-lived tracers that were measured on the aircraft that could tell us whether we're really seeing a separation between boundary layer air and not, although ozone seems to be a good potentially metric for that. And then just a sort of final shot here. Operating in an incredibly wet environment while you're measuring water can be a hazard, and one of the complications, this is a ballast plate on the WB-57 that upon landing had condensed enough that we were able to actually build a snowman in Guam. So I, being the in situ person, The instrument is always constructed by a team, so not just me, but the group, in particular Laurel Watts, Steve Sikora, and Rich McLaughlin, the engineers that really make it all work. My thanks to the Atrex and Poseidon science teams. None of this would occur well in a vacuum. And the ideas that we have and the measurements that everyone else makes all go together to try to do the science that we do. Ken Jux from the NASA Upper Atmosphere Campaign provided a lot of funding for this. And then the pilots and crew of the aircraft. And I would be happy to take any questions. Yes, Eric.
So I'm pretty sure I've asked you this before, but and the answer was no. But so you've looked at the Atrex data in the same way as the Poseidon data in terms of the ozone distribution.
I have done that.
I think you can hear me.
It's being cast. So the question is, have I done the ozone cloud analysis that was performed for Poseidon that I showed on the larger Atrex data set? And the answer is yes, I have. The ozone measurement from 2014, the precision was something of an issue, and it tends to get pretty smeared out. It's harder to say exactly what. We're going to look at it again and see if there's anything we can do statistically to pull information out of that. By and large, we wouldn't expect to ever really see those low values because of the types of clouds that we were looking at. But the ozone data there is more of a broad smear from sort of -5 parts per billion out to 40 parts per billion. So it's not quite.
What about the temperature distributions in cloud and out of cloud? Have you looked at that in the Atrex data?
Have not yet. That is something to go back and do. I think I looked at it for a different perspective, but haven't gone back with this in mind to look at that.
Yeah, I thought that was really interesting.
Yeah.
You're annoying, Bill.
No. So I got two questions. Eric, so this question of in-cloud versus out-of-cloud temperature, the clouds can make it cool also.
Yes.
Radiatively cool, so that could be another mechanism
That's true.
where you get colder temperatures.
That's true.
These clouds are heating.
They're actually,
On tops of clouds, though, you get radiative cooling, don't you?
On top of a really thick handful of clouds. That is probably too thin.
yeah.
Okay. I don't like your trajectory results. So you compare the temperatures directly, and they look reasonable, right?
Yep.
And if anything, at the coldest temperatures, they're a little bit warm in the reanalysis.
Yes, which you would expect.
You'd expect a little bit more water vapor. So this systematic underestimate of water vapor in the
Not necessarily, because yes, although the temperatures at which we're measuring them and the temperatures the reanalysis showing don't map in exactly that way. Because when we're doing the trajectory analysis, we're actually going back along the trajectory and finding the coldest temperature, which was frequently colder than the temperature, I mean, it was colder than the temperature at which we were
fair
measuring.
enough. But this suggests that the temperatures you're measuring, or the ECMWF temperatures are reasonable, or is this?
Are reasonable. So historically, one of the things is that you looked at ECMWF temperatures and they showed a cold bias relative to reanalyses, relative to satellite measurements and things like that. But once they started, as I'm sure you know, assimilating like the GPSRO data and things like that, they took a step up and are much more reasonable. So the only thing that's really different here is that we're making a measurement in, these are 1 minute average measurements. So there's significant variability, just precision type of thing within a grid model box that's not being captured and really responsible for that. But really there was no significant bias until you got to those coldest temperatures. And that's simply the case that the ECMWF is not capturing the subgrid cold, small scale cold processes, wave driven temperature variations.
So tell me again, what you make of this difference between the observed PDF of the water vapor and the back trajectory? It's a systematic difference. What do you make of that?
back trajectories, or these are coincident?
These are just coincident.
More water's
These
getting
are,
through-
but the,
more
Right.
water's getting through than you'd expect.
Right.
From just minimum saturation.
right, right, so it's,
No, well, you're right. So when we look at this, this comparison, this says that if you were to take all the water out just at the coldest temperature that it reached, you'd end up at sort of 2 parts per million in this case. Whereas when we make measurements above the highest clouds, final dehydration types of things, we see something that's more 2.5, 2.7. So we're seeing more water than you'd expect based on that coldest temperature.
right.
Yeah,
So-
this discrepancy would be even bigger.
Right,
Because of these temperatures.
right.
No, I understand that, but so is there a mechanism for moistening things along the trajectory or something, or what?
Oh, no, it's just that
You're not 100% efficient in dehydrating.
you're not as efficient. So when you reach, this is the minimum temperature. The plot on the left is the minimum temperature along the trajectories, and so that was typically occurring down here at 187 Kelvin. So we just suck all the water out to that value, and the argument that I'm making is that these different processes that we've looked at say that you don't get to do that because the atmosphere isn't perfect in that regard. So sometimes it'll hit 186.7, you'll be at 140% relative humidity, and you won't even form a cloud. Or you'll form a cloud, but you won't suck all the water out before you actually start to warm up. Or you do, but you don't actually get all the water to settle out, and some of it is still sort of carried along. Then sublimating and rehydrating. So that would be one of the sort of the rehydration.
Troy, you showed the long-term record of water from Boulder with the significant drop around 2000 as well as other ups and downs.
Yes.
Do you know of a good explanation for those variations?
Well, the analysis that Bill and Eric and Andy Dessler and have done is that sort of a lot of that variation, the interannual variability, is due to changes in the temperature of the tropopause. It's the primary governor. So all the things that I'm talking about are sort of secondary effects on that tropical tropopause temperature really sets the interannual variability as well as the seasonal cycle in water vapor reaching the stratosphere. And it does a really good job of capturing that in anomaly space. So, if you basically take the average out of the satellite and the average out of the model, they agree quite well. If you put those back in to get the absolute values, they tend to have something of an offset, which I then argue is because the model doesn't do a good job of capturing some of these smaller scale processes in dehydration. But this is really, it's temperature controlled. There's the QBO, ENSO type effects and things like that that are all feeding into it that affect the temperature of the particularly Western Pacific, although sometimes Central Pacific, tropopause, where the lowest water vapor really generally gets set. Is that a fair characterization, Bill?
Yeah, but I think this is still not well understood. That's
No,
a simple answer.
no. The precipitous drop,
The
not.
drop, but also this increase prior to 19.
The trend,
Prior to 2000.
Right.
That's still not understood.
right.
Well, this is where Boulder's where they made the measurements. There are not other long-term measurements that go back to 1980. So this is the only record. And after about 1990, then there were satellite measurements. Well, the satellite shows the drop and the other variability, but not this. It doesn't have the left-hand side of the time series.
Right. So it
The mid-90s, right?
missing this part.
Where you're at, where you're
So-
after the volcano.
So there and forward.
You are supposed to.
Yeah.
More questions? All right, let's thank Troy again.